Okay, so welcome to this special lecture. It's called the Chandrasekhar lecture by Professor Tom Lubensky. So before we start the lecture, our director of ICTS, Rajesh Gopakumar, he will give us a short overview of what ICTS is about. And then Professor Sriram Ramaswamy will introduce Tom, and then we'll start the lecture. So, Rajesh.
Yeah, good evening, everyone, and welcome to this special Infosys-ICTS Chandrasekhar lecture by Professor Lubensky. The Chandrasekhar lectures are part of our flagship lectures in the physical sciences, and we've had many eminent scientists give these lectures, and it's a pleasure to welcome Professor Lubensky to give these at ICTS. Before the lecture, I'll just give a very short overview of what ICTS is, directed mainly at the people who are here for the first time. ICTS is a new institution. It's a new center of the Tata Institute of Fundamental Research, and but with a very special mandate. And this mandate is, in a way, the interweaving of these three elements. There is, of course, the research, which, like all the components of TIFR, we lay great emphasis on a strong research profile of our faculty. But the new ingredients are the programs, of which this one that many of you are part of is an example. We function in many ways like the KITP in Santa Barbara, or in mathematics, the MSRI, and other institutions like that. But as you will notice, there are significant differences from any of these. So we've sort of combined different ingredients from many of these peer institutions to come up with something that's especially relevant in the Indian context. And but anyway, this makes it, I think, a unique institution, certainly in India, but perhaps even internationally, and I think has a lot of possibilities for Indian science to sort of develop Indian science. So we see ourselves in that sense as a hub or a national facility which will bring together the Indian scientific community. And finally, the third ingredient is the outreach, which I'll say a little bit also about, which we do vigorously. And these three are sort of combined in the sense that some of our researchers, but not necessarily always, are involved in the organization of programs. And but nevertheless, the programs feed into stimulating research at ICTS as well. And often the visitors in our programs end up giving some of our outreach lectures and so on, often involved in that, and so are our own researchers. So in that sense, these are sort of not disjoint activities. This is the campus. It's a new institution, as I said, in 2012. This was just a gleam in the architect's eye, but it has since materialized. By 2017, it was completed and taken the shape that you see it now. It's not a very big campus, as you might have already seen, but relatively self-contained. And you have, or probably will see, the facilities very soon, including our iconic library building, which is worth a visit. So, let me say a few words about the research and the programs and so on. The research areas at ICTS are currently the following over here. We don't have any departments. We are sort of loosely structured groups, and we like to have researchers with very strong core strengths, but who can talk across these groups. So in mathematics, which is where we have actually been hiring many people recently, we have areas such as dynamical systems, PD, big data, geometry and mathematical physics, probability theory in some ways, intersecting with statistical physics. And in physics, we have astrophysical relativity. The LIGO group here has been very active. In complex systems, this is sort of a catch-all term for condensed matter physics, statistical physics, fluid dynamics, biophysics, and so on. And finally, finally a group in string theory, quantum field theory, and related topics. The programs, as I said, are very varied. I like to emphasize that ICTS is not a conference center or a funding node, but as I said earlier, it's a science hub, and we hope that the ICTS programs can catalyze some fundamental transformations in Indian science or Indian scientific research. And the uniqueness of ICTS programs comes from its format, its duration, the way it's organized, and the directions the programs take. So very quickly, the format, there's often a pedagogical component to our school, to our programs, so that younger researchers, especially ones who wish to enter a new area, get a bit of a fast track. We archive all our talks so that even those who haven't been able to make it to these meetings are able to either watch them live stream on YouTube or later see it on our YouTube channel, ICTS Talks, which has now over 6,500 lectures. So it's a very vast repository of very valuable high-level talks. And in that sense, it creates a certain knowledge capital wealth for not just the whole country, for the world. And in many ways, having these programs is something cost-effective from the Indian taxpayer's point of view. The durations, the programs are often 2 weeks to 2 months, or perhaps even a semester long. And it gives, therefore, an extended opportunity for people to spend long periods together and for younger people to interact with some of the best scientists. So all the young people out there in the audience for this program, make use of this opportunity. You have excellent experts here, and you are having breakfast, lunch, dinner with them. Catch hold of them in the cafeteria, outside lectures, and make the most of the opportunity to talk with them and learn, because often out-of-classroom experiences is often the most valuable one. So this is also a sort of accidental side benefit of our being a little bit sequestered away from the city as well. So please do make the most of it, but also don't hesitate to go out if it gets too claustrophobic. So we are a node for various international cooperation with other institutions, notably the ICTS ICTP School on Quantitative Biology, which has been running very successfully, and various others. In terms of the organization, the program proposals are an open proposal system, so any bunch of academics from around the world can put in a proposal, and then there's a 6-month window for which one puts in, for which there's a call for proposals out for 6 months. So currently, end of June is the deadline for the 6-month window starting October 2020. Once the proposals are in, they are vetted by a program committee and then actively shaped by the leadership at ICTS. And often we play an active role in the process of shaping the programs. Sometimes we rope in other people into the organization. We try to ensure that the organizers have an adequate and broad lecture pedagogical component. Sometimes we suggest new topics, or broaden the scope, or narrow the scope, integrate with nearby disciplines using the memory of past ICTS programs. So memory is a very important feature, because We like to have programs which build on previous ones. We like to have organizers form long-term association and remain engaged with ICTS. So these things distinguish ICTS from being just a passive conference body. In terms of directions, again, we play an active role in trying to be a platform for new initiatives, directions which are less represented in the research agenda of the country. And as I said, we try to bring together often experts to brainstorm so that perhaps new directions and new ideas can be born out of that. And in some cases, we even try to make efforts to connect with industry and, in general, open out the channels of communication which sort of connect in a healthy scientific ecosystem, which should connect fundamental science to applied science, to engineering, and ultimately industry or the real world. In terms of numbers, we had over 150 programs and 70 discussion meetings, and nearly 15,000 participants. At the moment, we are sort of reaching a steady state of about 2,000 participants per year and about 30 program plus discussion meetings per year. And that's probably the limit in the sense that we are having a full calendar year round, and that looks like the asymptotic value. We have these special signature lectures, the Chandrasekhar, the Ramanujan in mathematics, Turing in biology and computer science, and also standalone special lectures like these. And the 2019 calendar is full, 2020 is full all the way till October, and as I said, we're inviting proposals now for the period from October 2020 onwards. The sampling of various programs that have been held, as you can see, they span a very wide spectrum in the physical sciences, in the mathematical sciences, even in economics and so on, but computer science, etc. So it's broader than what researchers at ICTS necessarily work on. So in that sense, theoretical sciences is very broadly interpreted and sampled. Finally, about outreach, we have had a number of public lectures which are by eminent scientists, and once again, these have been very popular. And now our YouTube channel has over 20,000 subscribers, and the majority of the 2 million views, of course, have been for the popular talks, but some of the technical talks have also been surprisingly popular. We are active on social media. We had special set of initiatives around the centenary of general relativity, and similarly, we were part of the mathematics of planet Earth. The main flagship outreach program now is something called Kaapi with Curiosity. We just had one last Sunday. It's held monthly at the planetarium and in the city, and it consists of talks and talk with a lot of time for discussion. And these are by scientists, not just from Bangalore, but from outside as well as often ICTS program visitors. And it gets a very big turnout every time. 300 to 400 is sort of the norm. And it's been running successfully for nearly 3 years now, and something we are very happy about. And we've had these talks on, again, a variety of topics in physics, mathematics, biology, climate science, space science, and so on. As part of our 10th anniversary, we had some very special events, including a very stimulating scientific event. The ICTS had 10. There was a panel discussion and public lecture on the usefulness of useless knowledge. And finally, a rock concert by Kipton, which was held in the foyer outside, which drew visitors from as far away as Pune. So if you haven't seen it, maybe you should watch it on our YouTube channel. So thank you again, and hope to see you sometime once more at an ICTS program. Now I'll hand it over to Sriram, who will introduce the speaker.
Hi. It's a very great pleasure indeed to introduce Tom Lubensky. Tom has been to Bangalore at least a couple of times before, once for StatFizz and once for a liquid crystals meeting many years ago, maybe more than that, I don't know. Tom Lubensky is a condensed matter and statistical physicist, theoretician of extraordinary distinction. He has worked on the physics of broken symmetry in liquid crystals and quasicrystals and many other interesting materials. Most recently, of course, he's been working on the things he's going to tell you about today, which I won't summarize at all. I know Tom. I had the privilege of being a postdoctoral fellow in his group in the 1980s, which is a wonderful experience. Tom, I should also add, is exceptionally distinguished in terms of formal recognitions, such as the Buckley Prize of the APS for condensed matter physics, and he's a member of the US National Academy of Sciences, to name just a couple of his amazing distinctions. Tom's research style and way of talking about physics is characterized by precision, a fondness for mathematical elegance, and at the same time, he indulges other people whose way of talking about things is less precise. And it was a wonderful experience working with him. I should also tell you, something else that characterizes him. Tom is deeply interested in music. He's exceptionally fit. He arrived yesterday after not getting a taxi at the airport. Not being picked up at the airport. Got a taxi on his own. Arrived, took a nap, went to the pool and swam, or maybe in the opposite order. So this tells you a little bit about him in other ways. I won't spend more time on describing him. I'll let Tom take over. So I give you Tom Lubensky.
Yes, it's a great honor to be here. As Sriram said, this is my third time here. The first time was really, I have a little levity right now. The U.S., India owed the U.S. government, the Department of Navy, a pile of money, which the agreement was that it would be paid in rupees, and they don't market very well in the States. So Shashidhar, who used to be here, arranged for us to come to India on what I would call one of the world's biggest boondoggles. We went to the embassy in Delhi, and the first thing we did was to go up to the accountant's counter, and we were given a suitcase this big, like that. Literally, he opened it up, it was full of rupees. And the deal was we were staying at $300 a night hotel rooms, and we had to pay the bill every day in rupees like that. I felt like we were criminals, but it was a wonderful time. Anyhow, I know it's a special occasion because, Sriram's in his red Nehru outfit here, which is a little unusual. And I also should say, one pleasure about being here in India is that I think half the people in the world who read my book are somewhere in this subcontinent. Okay, so today I'm going to talk about a relatively new field, actually two relatively new fields. Over the last 10 years, there's been enormous advances in mechanical engineering, in advanced material science, and in topological physics, all of which are going to come together in this talk. You all know of the advances made by Charlie Kane here and Jean Malie, who got the Fundamental Physics Prize this year with $1.5 million each, and also got the prize from the outfit in the Basque Country in Spain. I've forgotten which one that's called. So they're very popular now. So these are the people I've collaborated with, and they will appear in some of the references I make. But Charlie, of course, was the most important one. I'll tell you a little bit more about that when I get to it. And of course, in the background is my best collaborator, James Clerk Maxwell. This work I'm going to present really goes back to a paper he wrote in 1865. Okay, so the first I'm going to talk about metamaterials. So these are the first metamaterials that I know of. Notice the time, 2001, which is not that long ago. Well, at least for me, it's not that long ago. The idea is that you try to make materials which perform specific functions And they're materials which you would not find naturally in nature. In other words, they're not like sodium chloride or nickel or something like that. This particular one, as you can see, has a length scale which is about 1 centimeter per unit cell, and it is a microwave index of refraction system that cloaks. You know, it has what they call a negative index of refraction, and this was the first one that was made. Fast forward to 2012. I think that's what the 12 stands for there, 712, maybe it's 17. 17, it's 17. So this is a metal material in which, you know, they have, I forget exactly how they do it, probably cut it with a laser, these different textures in a unit cell, repeating them. You have chiral ones, and et cetera. And you vibrate them, and they have a frequency response, and they find that you can create these things so that they have one-way propagation of sound, not light, around the corner here. Now, how are these made? Okay, now that's metamaterials. Now the next subject is 3D printing, or it's called additive manufacturing. This is a field that has taken off. It will be not very long before you will not be able to fly an airplane that does not have components in its engine made with 3D printing. They already make entire helicopter engines by the printing process, and I'll show you a little bit more about that. And I'll let you know in a moment why I'm interested in it. So the simplest 3D printing process has a delivery mechanism for different materials which will come in a molten state and then freeze very quickly. You deliver them at a micron at a time. This is a 2-gun material, and it's shooting down polymer, and it will make a structure whose details are hidden in some CAD machine or CAD program somewhere, and it will grow layer by layer. This is a famous one that appeared somewhere not too long ago. These Eiffel Towers were pulled out of a polymer melt, which was subjected to lasers, you know, crossed in such a way that you get an intensity increase, and you polymerize the polymer as it comes up like that. And, you know, people make all kinds of things, you know, fanciful spheres, 3D Escher things, you know, designer shoes, and people's ears, for example, you can make with these. And you're going to find, and this is going to revolutionize prosthetics in medicine. This is a part in the LEAP engine, which was a collaboration between GE and the Safran group, a French firm. The story of this was that the engineers who can do marvelous things with computers now designed a new pathway for the combustible gases that went into the combustion chamber. And they found that this thing would increase the efficiency of the engine by a measurable amount, you know, several %. And then they went to mechanical engineers and said, well, make this for me. And it involved something like 23 parts and lots of screws. And the net result that it just wasn't economical. It would have added too much weight to the engine and it wouldn't work. So this guy, I never can touch these things in the right way. Esteshami, who was in charge of the development of new engines, thought of the idea of using additive manufacturing. They had a firm in Ohio that had used 3D printing for prototyping. In other words, they would make a piece to see if it worked, and then it would go to the standard subtractive manufacturing techniques. But they asked him if they could make this thing with the additive manufacturing and whether or not they could scale it upward. And the answer turned out to be both. And in addition, the part that they made with the 3D manufacturing was lighter. It was apparently more durable, and it worked perfectly. So this, and actually, I was co-chair of the National Academy study of material science and engineering, and they, 3D printing is taking over a lot of what people used to do. There's lots of research to be done on it. So how do industries make this advance? We have all this competition amongst countries now to see who can have the best scientists and the most advanced science economy. It turned out that they went out and bought firms in Germany and in Italy of all places, because Italy had a very strong relation between the engineering schools and actual industry. And now, if you can go to a web page of any of the makers of engines like this, and they will have a web page showing you how they do the additive manufacturing. Now, if we, so I want to just stop for a moment, and if I'm lucky, I can show you a YouTube thing. Let me just see if that will work. Just see here. Yeah, I think it's going to work. Okay, so this is unabashedly a YouTube thing that's advertising it, but it'll show how this 3D printing works, which has a bed of granular metal material, which they melt or center with a laser beam or an electron beam, creating it layer by layer. So this is about 2 minutes long.
Is there audio?
Excuse me?
Is there audio?
No. There is audio, but I don't. It's not so important. Well, it probably is important, but go. Oh no, I guess maybe this is what I want. We're not getting the audio, or maybe I turned the audio on. Yes, I did turn it on.
It uses selective powder deposition process, SPD for short. SPD is explained in details in our other videos, but basically you selectively pour, build, and support powders into a crucible.
Oh, shoot.
Add an infill metal
this
and
happened
bake
to
it
me
in a
last
kiln.
time. It's not going to work. Sorry.
Let's look at each step. Here we pour metal powder.
Okay, here we go. Here we go.
But you don't see much because the crucible is opaque.
Yeah.
Let's take a petri dish and pretend for a second it's a crucible. Here we can see how the powders are selectively deposited.
This is a different one from what I thought it was. For some reason, YouTube will not allow you to keep an image up or program up for a long time because they lose the advertisements. Anyhow, you'll see a little bit about how this works. Okay, this is not the one I wanted to show. What I'll do is, at the end, if there's still time, I'll show this. It's actually fairly interesting to see how it's done and with what precision. So let me stop this. They moved me forward to a place I didn't want to be. I apologize. Where's my thing here? Okay. Okay, so now obviously I'm not going to tell you about how I'm going to build jet engines, but these are the kind of things I'm interested in. These frames is what James Clerk Maxwell called them. He wanted to know, when is a bridge stable? So this is the Warren Truss 1848. It's actually mentioned in his article that I mentioned. And so he posed the problem in the following way. I have these beams, which we can think of as being constraints on the position of the nodes in the system. And he wants to know what design of struts or beams and nodes will be stable. So he argued that the nodes can displace in d dimensions in d different directions freely with no energy if they're alone. So if I have 2 points here, then I have 6 degrees of freedom if they're in 3 dimensions. But if I tie the 2 points together, then I only have 5 degrees of freedom because they can't stretch like this, but I can have 1, 2, 3, 4, 5. If they're dimensionless streams, this actually has an extra one to spin like that. So he said, well, okay, let's say that the total number of zero modes or floppy modes of the system, or mechanisms as the engineers call them, and then we'll start adding beams. And at some point, the number of beams will equal the number of degrees of freedom, and at that point, you no longer have any zero modes. The number of zero modes, or the mechanisms, is equal to the number of degrees of freedom minus the number of constraints. So that was Maxwell's 1864. I think I said 65 before. Now, the other end of the coin is that with the 3D printing, you can make lattices like this now, all kinds of things. From a scale that basically is happy at several millimeters down to, if you're very careful and believe the people who made it, this length right here is 500 microns. So this down here is probably, at the 10 micron scale. So you can make a lattice that has a structure that you can't see unless you magnify it. And the question is, can you design the structure to have unusual mechanical properties? And the answer is yes. Here, for example, is one. This is, you'll recognize it as a diamond lattice. There's a diamond lattice composed of beams that are thickened at the middle and come to a point where you have a very soft node. And the effect is that there's a high energy cost for compressing the beams, and you've tried to minimize as much as possible the force required to bend two neighboring beams. And the reason for that is that if there were no rotational restoring force at these points, then this material would have a non-zero bulk modulus because of the arrangement of the beams. A diamond lattice has that. So it will resist compression or isotropic expansion, but all of the shear moduli in the system are zero, and the thing would fall apart underneath. However, if you put a little bit of bending in it, then there is the shear moduli will be stabilized by that bending force. So what you have then are 5 very soft modes and 1 hard mode in the system, and they call this a pentamode system. So I'm going to be interested in a particular variety of these types of materials, which can be made, as I said, but they do have the flaw, at least as far as the theory I'm going to present, that all real materials have these bending forces in them, and we want to make them as small as possible. And if I have time at the end, I will tell you how we can deal with going to putting those parts in. So here are a bunch of lattices, which I like to call Maxwell lattices, and they have the property that their number of neighbors, their coordination number, is equal to twice the dimension. So if you ask how many constraints do bonds impose upon the sites of a lattice like this, it's equal to the number of constraints is 1/2 z, the coordination number, times the number of sites. And if you want 1/2 z to equal 1/2 zn to equal dn, then you want z to equal twice the dimension. So in 2 dimensions, if you have a lattice that has a coordination number 4, it's going to be one of these, what we'll call a Maxwell lattice, one that is just on the verge of stability. Now, in order to have it so that every single site has exactly 4 bonds coming into it, we need to put things under periodic boundary conditions. So I'll first study what happens when you have periodic boundary conditions, and then ask what happens to the edges when you cut them and make strips originally. So, we're used to thinking of lattices that are really symmetric, like the square lattice and the Kagome lattice. These 2 lattices are special because they have straight lines of bonds, which have special properties called states of self-stress, which I'll explain in a moment. But each of these can be distorted. This one, actually going from here to here, is from the standard Kagome lattice, what we call a twisted Kagome lattice. This is a transformation that occurs simply by twisting neighboring triangles through an angle alpha relative to each other. And in the process, not a single bond has changed length. So this guy has a macroscopic elastic mode of 0 energy. And we'll find that that's a general property of these. They also have lots of interesting phonon properties, which we'll get to in a moment. Here are 3D versions. This is the pyrochlore lattice, which is familiar to some of you, I think. And each site has 6 neighbors, which is what you need in 3 dimensions. And here is a distorted Kagome pyrochlore lattice. And this guy has this shouldn't have an arrow there. This one does. This one has topological properties that this one doesn't. And this one has topological properties this doesn't at the moment. So we'll get to that. But these are the lattices that I'm interested in. Now, I'm going to show you a wonderful, or not an animation, this is a demonstration using a toy model, literally a toy model made from toys, which will encapsulate all of the properties that I'm going to tell you about mathematically. If you remember this, you will have gotten something out of this talk. So let's see, this is prepared by my former postdoc Xiaoming Mao, her husband Kai Sun, a student, Zhengren Zhu, and a postdoc Zeb Rocklin, who is now on the faculty at Georgia Tech. Okay, so we're going to see a, not going, have to keep going. What? Okay, I think it's going. It's going, okay. Okay, so this is a sort of a tinker toy model. It actually is a generalized Kagome lattice, though it's a little hard to tell because the rigidity is built in with strong bending forces in particular directions. Now notice they pushed on one side there. Notice that you got an invagination which is localized on one site. So that means that in order to be able to have a soft area at every point along the way, I have to have lots of wave numbers in order to be able to create that. And what's happened there is that there is a zero mode, a zero energy mode for every wave number along the surface. Now, they went to the other side. I don't know how carefully you were watching, but on both sides of the system, you had the same behavior. There was a zero mode on both sides. Now they're doing a transformation here, passing through a point where you saw those red lines. Those represent the transition from one lattice to a topologically distinct lattice. And now you'll see that this topologically distinct lattice has different properties. The shearing transition they just did was probably a zero energy mode. But now watch this. This is the zero energy mode of the bottom surface now. Perfectly rigid, the bottom surface. Before it invaginated when they pushed with the same force. Now they're going to go to the other side, and it's going to be easier to push in. So it's not so obvious that this lattice actually has a geometric polarization. In other words, it has a P1 symmetry that you can't see too well. And it's that property that gives this thing what we call a topological polarization. And that having a topological polarization which points normal to the edge will transfer a zero mode from one edge to the opposite one. And that's what happened here. So we started off with a zero mode, and I'll give you the reason why that count was such in a moment. But you had two surfaces, each of which they look different, but they have the property that there's one zero mode per wave number along each side. You turn on the polarization and you take the zero mode for each Q and move it to the other side. So, that's one thing to remember. Now we're going to go. Now, here is a three-dimensional version of what we were talking about, designed by my postdoc Olaf Stennel, and Charlie Kane is on in this as well. It's a slightly distorted pyrochlore lattice, and this is the lattice that was actually built by the group at ETH, led by a guy named Bilal. Here is the material they made. They made this with a two-gun additive manufacturing machine where there was one polymer that was very rigid and gave you the rods, and then a very soft polymer that gave you the nodes. So there was an attempt here to minimize as much as possible the bending force to do that. And then they did a simple experiment. But first of all, the theory said that you'd have a soft surface here and a hard surface at the bottom. In other words, rigid and soft. And notice this has the peculiar property that if you cut it in half, the top surface is still soft, and the bottom surface, there's a new bottom surface which is rigid, and a new soft surface is rigid. So, you know, if you're writing a proposal, you might say, well, I've got a system here that's going to be soft forever, and if you keep on filing it away, it's going to stay that way. Not so successful so far. Anyhow, they did an experiment of invaginating the two surfaces. So here's the load, and this is the indentation, right? The red here, the orange refers to this surface, and the blue refers to that surface. So here you can see that for a given indentation, the load required to produce that indentation on the soft surface, the blue one, is less than it is on the big one. So that would not be the case for a standard solid. Standard solid would be controlled entirely by the elasticity, in which you have positive definite elastic moduli, and you would have the same behavior on both sides. Here it's different, so this means that this thing, though it is not the perfect Maxwell lattice that I talked about because of the bending forces, it still retains a memory of that special behavior that comes from the Maxwell lattice. Okay, so here are the properties of the Maxwell lattices. We're going to look at the phonon spectrum, and we're going to find that depending upon the geometrical arrangement of the sites and rods, sites and bonds, you can have a phonon spectrum that is either gapped or ungapped. So what do I mean by gapped? I mean that except for the point at wave number equals 0, where the phonon velocities have to be 0 because of the translational invariance, every other phonon frequency in the system is non-zero, which means there's a gap everywhere. Some of these lattices, the original Kagome in particular, has ungapped regions, in other words, lines of zero modes. Now, it's when you both have when systems are gapped and there are no zero modes, are sometimes called isostatic. Now, what we'll find is that there are always zero modes at free surfaces in these lattices. So once you take the periodic system and cut it, then the exposed surface will have zero modes. The topological properties of the edge modes are determined by, the edge mode properties are determined by the topological properties of the bulk phonons. That's true of the electronic system. Topological change moves zero modes from one free surface to the opposite. That's what we just saw. There's always a non-zero elastic mode of zero energy, 1 in 2 dimensions and 3 in 3 dimensions. And in addition, you have the possibility of localized zero modes, which exist at wave numbers in the interior of the bulk brittle one zone, and these are called Weil modes, or sometimes I forgot the name now. Dirac modes. Dirac, that's what I wanted. Okay, so what I'm going to do is to spend a little time now with the mathematical preliminaries. This is really an exercise in linear algebra. Most scientists have to take a course in linear algebra, so I hope that you're not totally blown over by it. And we'll look at the bulk modes and non-topological Kagome and twisted Kagome lattices. Then I'll talk about the Maxwell-Kalodine and surface modes, a theorem. It's this thing, and what they have to say about the surface modes. Then I'll tell you how we make the topological lattices to give them a non-vanishing polarization. And we'll look at the zero energy modes of free edges and domain walls, talk briefly about other three-dimensional things, and maybe have time to talk about a route to standard elastic solids. The Suess-Schrieffer-Heeger model and mechanical graphene are really wonderful models to increase your understanding of what goes on here. But I doubt we'll get to that by the end of the hour, or whatever my time is. Okay, so this is the Maxwell-Kalodine count. This is a theorem, which I'll show you, I'll derive for you in a moment. Let's imagine we have a frame here, and what Maxwell says is that the number of zero modes is the number of degrees of freedom minus the number of constraints. So here's a frame with 6 sites and 7 bonds. So Maxwell would say that there should be dn, that's 2 times 6, minus 7, that's the number of bonds, which is equal to 5, which is equal to 3 plus 2. We're good at numerology here. So 3, this is a lattice that's sitting free without external boundaries imposing any constraints. So there are 3 rigid displacements of the system that cost no energy. You can move it this way, you can move it that way, or you can do that. So there are 2 left over, and these are the floppy modes or mechanisms that involve changes in the geometry of the system with no stretching of no bonds. So clearly I can take this guy and rotate it upward. Somehow we lost the site there. Or I can do a shear like that. Here's another example where n is 6 and nc is 8, leaving us with 3 plus 1 degrees of freedom according to Maxwell. Again, the 3 trivial ones and 1 zero mode. So this guy sitting here I still have this sort of shearing mode of the square that costs no energy. I can add one more bond, and that saturates the system. Now I have n is 6 and number of constraints is 9, leaving us with 3 zero modes, which are saturated by the trivial ones. But this guy, I added a bond here, but I could have added it across the other site. That would give me a zero mode here, which would violate Maxwell now, because Maxwell would have said that there's something zero here that doesn't work. So this is a zero mode, but this guy has a new property which we didn't see before, and that is the property that it is possible to create stresses in the bonds, non-zero stresses, such that there are no forces on the sites. So that's what the Kaladein called a state of self-stress. The simplest version you can think of, I should have drawn a picture of it, is imagine you have a ball and spring polymer, or just a straight line wrapped around a cylinder. Okay, and then I just expand the inner cylinder. What happens then is I stretch all of the bonds, but I reach a state where there's no force on the sites. Okay, so what happened here? When I went from here to here, this guy satisfies Maxwell. This guy apparently doesn't. But what I did was I added one zero mode to what was here and one state of self-stress. So that suggests that the relation of Maxwell, which was n naught is dn minus nb, should be modified simply by introducing the state of self-stress number s, so that n naught minus s is dn minus nb. And this is actually a theorem, at least for linearized displacements. And you can see this as follows. Let's let bold U here be the dn-dimensional displacement vector. So this is telling you the whole collection of displacements of the n sites in the system. And let F, which is the force, be the dn-dimensional vector of forces on sites. So remember that in d dimensions, the force can point in d directions at each site. So I have dn forces, and so it has the same dimension as U. Let E, or extension, be the NB dimensional vector of bond stretches. So that's, I tell you how much this guy's stretching. It can be positive or negative, but I just want to know how many of them there are. And T is the NB dimensional vector of bond tensions. Now, obviously, if I give you all of the displacements, I can tell you what the stretches and the bonds are. Right? So there's a linear relation between displacements and stretches. We call this, C is called the compatibility matrix. It's an NB cross dn dimensional matrix. If I give you the tensions in all the bonds, then I can calculate the force, Qt equals F. Strictly speaking, there's a subtlety here. There should be a minus F. The engineers look at loads as opposed to internal forces. And if you read the literature on that, you might get a little confused. Anyhow, this is a dn cross nb dimensional vector. Now, it should come as no surprise that these two are transposers of each other. It's easy to prove, but it takes a couple of lines. I can do that here. So what is the null space of C? There's a null space of C is a set of U's such that when C operates on it, I get 0. So if I get 0, that means the stretches are 0. And if the stretches are 0, I have no energy in the bonds, and so that calculates the zero modes. The dimension of the null space of C is the number of zero modes. What is the null space of Q rather? That's the set of tensions which give no forces. Well, that's just the definition of a state of self-stress. So the null space of Q is the number of states, or the dimension of the null space of Q is the number of states of self-stress. So now we can write that the number of zero modes is you can say it in various fancy ways. It's the dimension of the null space of C, or the dimension of the kernel of C. S is the dimension of the null space of Q. And the rank of Q and C are the same because they're transposers of each other. So we have rank C plus n naught. So rank, that's telling you the dimension of the space which actually gets transported to something other than the origin. Plus n naught equals dn, rank of Q plus S is nb. These are theorems from linear algebra. And the net results, when I subtract them, I get exactly this. Now, I could go through a few steps of algebra, but you can see here now that the energy of the system is a half k times the stretches squared, I can write the stretches as, let's see, the stretches as, here it is, C times U. So if I have E squared, I can write that as C transpose C times E, and I get then what's called the dynamical matrix, which is what determines the dynamics of the phonons. Now, I'm interested, I don't have to restrict our attention to this, but it turns out that it's a sufficiently rich field that I want to look at Maxwell lattices, which are periodic. And that means that Q, the wave number, is a good quantum number, if you wish. And this big matrix, which is dn by, well, I'm taking nb equal to dn because we have a Maxwell lattice. So we have this dn by nb dimensional matrix, which breaks up into subblocks of dimension of the unit cell. So for each Q, I have the number of zero modes at wave number Q minus the number of states of self-stress at wave number Q is equal to the number of degrees of freedom in a unit cell minus the number of bonds in the unit cell. And we can now apply the theorem that, well, this is the theorem that follows from the fact that I can write that there is a submatrix of dimension little dn cross dn, such that C operating on U of Q gives me E of Q, et cetera. So the Maxwell lattices we're looking at, we've chosen so that dn is equal to nb, which means that the number of zero modes always has to equal the number of states of self-stress. And that immediately tells us a lot about the spectrum of the phonons. So let's look at the Kagome lattice. So the Kagome lattice, this red here represents the zero mode, which I'll talk about in a moment, but ignore that and just assume it's the same as the blues. So this is characterized by grids of straight lines that go along the three directions of a hexagonal lattice. So remember, these things are under periodic boundary conditions, so you can think of them as being wrapped on a cylinder or on a torus, and ignoring any Gaussian curvature that comes out of that model. And so each of the straight lines of bonds carries with it a state of self-stress. And the number of those straight lines is 3 square root of n, where n is the total number, because it's just lines, it's not points everywhere. So that tells me that I have to have that many zero modes in the spectrum. And indeed, if you go and calculate the spectrum of phonons, this is what it is. If I go along the line gamma to m, I have a zero mode for every wave number that goes from gamma to m and in the two complementary directions. Here's what that looks like, what the lowest modes look like. This is the frequency, and this is qx and qy, and you have these knife edges coming down, straight lines coming up, and zeros everywhere. Now what happens if I add a next nearest neighbor bond? Then I'm adding extra constraints, and the Maxwell theorem, or the Calodyne theorem, takes a different form, and I no longer have zero modes. So this guy gets lifted up, and it looks like this. Gap the spectrum completely. Surprisingly, if I just twist the lattice like this, instead of adding next nearest neighbor bonds, I get the same thing with a gap here that's proportional to the sine of the twist angle that I put in. So now if I look along, if I look along m to k, then before I've twisted, I have this knife edge coming in, which you see up there. I twist it, and I get this. Now, if you live in a physics department, I think it's pretty hard to avoid seeing something like this at some time in your life. This is exactly what happens in polyacetylene. It's exactly what happens in topological insulators. You have a gap that forms. Once the gap forms, that means that you can't change the bulk properties of the system if you just have slow variations away from the state that has that gap. So there's a finite region of parameter space where the gap is there, and you have the properties associated with it. And that's why we say that the states that arise from this are topologically protected. And so what we're going to find in a moment is that the Kagome lattice with the straight lines of bonds, states of self-stress, is a transition lattice between one type of topological lattice and another one. Okay. So here, this shows one of the special properties of the twisted Kagome lattice. Here, I twist a little bit and I get this lattice. Now, I press on the top a little. What's going to happen? Well, it's going to continue to rotate the bond, so I go from here to here to here, and it costs me no energy to do that. Notice that the area has changed in going from here to here to here, and so there's no energy cost with an area change. So that means that the bulk modulus of this system is 0. The bulk modulus measures the energy that goes with changing the volume, the relative volume. And so this is what they call an ideally auxetic material, and it's an isotropic auxetic material. It has a negative Poisson ratio, which means that you push like this, or you pull like this. Normally you expect a bar, for example, to contract in this direction if you pull in this direction. And that's because most materials that you're used to dealing with have a bulk modulus which is larger than the shear moduli, and that makes the thing basically, if you pull steel, it basically stretches at 0 volume change. Okay. So that was the soft mode I was telling you about, the nonlinear soft mode. Okay, now let's ask what happens. Is somebody monitoring my time? I tend to. Oh, great. Okay, so 7:30 we'll be done. I have 16 minutes left. Oh, very good. You're the official timekeeper? Okay, so now we want to cut a strip. I'm going to, let's see, is this water for me? Yeah, good. So now we want to investigate the surface modes. So let's take the Kagome lattice like this, and imagine this thing wrapped in a torus, and I take a razor blade and come along and I cut the 2 bonds per unit cell needed to separate this surface from that one. So if you look carefully, you can see that these 2 dotted lines connect over here to this region right there. So in the process, what I've done is I have removed 2 bonds per unit cell on the surface. Therefore, I've reduced the number of constraints, and normally that would mean that I've reduced the number of 0 modes. But I've also killed 2 states of self-stress per surface unit cell. You see, coming down here, I have this straight line that goes like that, which would have been connected under the periodic boundary conditions, and another one going in the other direction. So I've changed both the number of constraints and the number of states of self-stress, the same number, so the net result is the number of 0 modes remains unchanged. So this guy still has the spectrum of that. Now let's go to the twisted Kagome lattice. Here, I've still cut the 2 bonds per unit cell, but I have not killed any of the states of self-stress because there were none. So what happens then is that the number of 0 modes in this case actually is equal to the number of bonds I cut, which is 2 bonds per unit cell. So what this tells us, from the Maxwell-Lattices theorem, is that there are 2 modes per unit cell. I've created this on the surface. I've created a strip. I don't know where those 0 modes are. Now, so there are going to be the standard twisted Kagome that we looked at, we'll look at here, has the same behavior on both sides. There's 1 0 mode per unit cell on the top surface and 1 0 mode per unit cell on the bottom surface. Now, we can calculate what the inverse penetration depth is. So if I have, what we have are surface modes, and we know that there are surface modes in solids. In 2D solids, there would be the Rayleigh waves. There are the Rayleigh-Lamb waves that are important in geology. They are modes that are restricted to the surface and decay exponentially into the bulk. So we have solutions of the form, if the surface is along the y direction, so it's vertical like this, then there will be an exponential decay in the x direction, and we should put a kappa here. So what we did, you can calculate. A nice thing about things like this, it looks like it's a hard calculation, but remember that the dynamical matrix is Q C transpose C. So all I have to do is to look at the zero modes of C with an exponential decay, and that's a trivial thing to do. And so as a function of the alpha, you get these lines that go like this. This is the Q along the surface. This is the inverse penetration depth. They have the same units. And so these are for different values of alpha. I won't go into why this thing's curving upward, but all of them asymptote to the same straight line down here at small q. And that is because at the long wavelength, in other words, small q, this lattice is described by continuum theory, which you can go look up in Landau and Lifshitz. And you can look at what the velocity of the Rayleigh wave on the surface is in that long wavelength limit when your bulk modulus is 0. And the calculation says that the energy is 0 and that the inverse penetration depth is exactly equal to the wave number along here for an isotropic system, which is what is the case for the Kagome lattice, the twisted Kagome lattice. Okay, so now, so far, all we've had are the twisted Kagome lattice, and it was, this is where the wonderful insight of Charlie Kane, who'd spent a lot of time on topological properties, came to the fore. It took me 2 years to convince him that there was anything topological here. I was laughed off out of the room several times, and finally caught him. And he had the following profound observation. The Kagome lattice itself has these 3 grids, and that complicates things. So he said, let's consider a lattice that has 1 grid, like this. So now I have only states of self-stress associated with these horizontal things, and just a single line of 0 modes in the Brillouin zone. Then what he does is say, okay, if I take this point and move it down, and that point and move it up, rotating things, then I go towards the twisted Kagome lattice, which we had before, and it is gapped everywhere, as you can see from this. Or I can do it the other way. I can move this one up and that one down, and I get this structure. And this guy, you can notice, is really, it's polar. It has no inversion symmetries or any, well, this one doesn't even have inversion symmetry. It's polar, which means there is a possibility of defining a vector associated with it that is, defines a direction in the lattice. Here it looks like we have 0 modes here, but that also is another thing that comes out of the predictions of this theory. What these modes are modes whose frequency goes as wave number squared instead of there's the wave number, which is what happens for phonons. So it looks like they're 0, but they go up to that. Just to emphasize, now it's tempting if you've come from the electronic world to say that, symmetry is what's determining this. Because after all, there is a symmetry change going from here to here to here. This guy doesn't have the polarization. But I can make 3 different lattices with P1 symmetry. This one is like this guy, this one's like this guy, and this one is like this guy. This is the only one that has the non-trivial polarization, topological polarization vector. The other 2 don't. So it's not symmetry that does it, and that's causes the electronic people a little consternation. Okay, so how do we work in properties of the bulk spectrum and find a relationship between it and the 0 modes in the system? Now, this really is a story that's going to take longer, and this will be a subject, part of the things I'll talk about over the next 4 days. But what you do is you can define a number of surface 0 modes along a surface, a lattice plane whose normal is G. That's the usual way that you define a lattice plane. And Q will be a vector along that plane, and G defines the direction perpendicular going into there. So you can express this C, and I put a surface here, meaning it has to do with the surface, and I'll tell you more about that in a minute, where Z is e to the IQ, Z is e to the IQ, G 2 pi over GQ, and I'm sorry, ZQ is that. Z is e to the IP over G going in, and the question is, can we find a solution where this actually decays instead of is imaginary? And the answer is yes, and this gives you the count. But you have to choose a unit cell which is compatible with the surface. So what we typically did, if you can see here. So here's a unit cell that has 6 bonds in it and 3 sites, and it's symmetric. So one thing you often do in this game is to assign charges. So if you assign charge 2 to the sites, because there are 2 degrees of freedom, and charge -1 to the bonds, then you have sort of a lattice that's like a sodium chloride, where you have sodium plus and chlorine minus. And you can ask yourself, does a unit cell you've defined have a dipole moment? And this symmetric one doesn't. But if I want to know what's happening on the surface, I need to choose a unit cell that doesn't have any bonds sticking out the end. And if you choose this unit cell over that one, you find that you have only positive powers of e to the iz going in here, or e to the iz, what did I call it? E to the izp, zq, or e to the iz, right? The z. So the z, if I have powers only e to the iq, or positive powers of z, then I can have decaying results going into there. If I chose another one, there would be 1 over z factors, and this theorem, which tells us that I actually am supposed to, with this integral around the unit circle of d by dz of the log of the determinant of c. The determinant of c gives you a mapping from your Brillouin zone to the complex plane. And usually this is the number of 0 modes in the determinant of C minus the number of poles. And you want only 0 modes, or zeros, not 0 modes, zeros of that, in order that you have only positive powers of Z. And that guarantees that the count that you're doing is counting the number of 0 modes and not the number of poles. So you can then break up this. Did I not write it out? Yeah. So you can then break up this thing into a property of this symmetric unit cell and a local polarization on the surface, which tells you the difference between this guy and that guy, which you can get by a gauge transformation. So just remember that we can calculate a RT, and RT in our case is 1/2. We can calculate the RT. It's by doing this integral. And then the RL has to do with how I have to move bonds to go from this guy. Where's my green guy? There he is. Okay. So if I want to create this unit cell, I take this bond and I move it up to there. So I moved a single bond, a lattice spacing, and that gives me a surface charge or dipole moment, which is equal to that lattice spacing, it turns out. So with all of that, we can go and ask whether or not we have the right answers. So here are various surfaces of these twisted lattices. So here is one where the polarization vector points in this direction, and the normal to the surface points down. So that shows that there's a fairly large overlap between RT and G. And the local charge or dipole moment coming from being on a surface cell, we also calculated. And it turns out that this surface has then 2 modes per unit cell, and the opposite surface has none. One of the inverse penetration depths comes in as the square of the surface wave number rather than linearly, and then there's another one that doesn't. When you go to these vertical surfaces, there are more sites per unit cell on the surface. There are 4 sites, and here is one where we have moved 4 modes, or rather 2 modes from the right side over to the left side, giving us 4 0 modes on this side and 0, and none on the other side. Here's one where we have 3 modes. Shoot. Oops, I went the wrong way. Where we have 3 modes on one surface and 1 on the other. So that's the story for the simplest cases. And well, one other thing. If I were to come in and take a slab which has RT as a polarization, and another slab that has RT equal to 0, and tie them together. Remember, the unit cells are all the same size the way I've done this. So I can tie together cells of different polarization, in other words, different rearrangement of the bonds, and have them have their cell endpoints match. So if I come in and I create a wall here, it gives me a zero mode along here. There has to be a complementary wall of states of self-stress because the Maxwell-Kalodine theorem still applies. It turns out now there's no surface here, so the RL parts disappear, and the number of zero modes if this number G dot R left T minus R right T is equal to 1, we have zero modes. If it's equal to -1, we have states of self-stress. Okay? And this is a calculation that shows that, but we can actually, the nice thing about these, if you want to treat the domain wall, you know that without, with the zero mode over there, I have a zero mode decaying away from a free surface. The same is true going the other way. I just tie them together and make the boundary conditions that they're locked to the same amplitude along the side, and I've got a well-defined domain wall zero mode. Okay, this is a little complicated. Let's see, your timer is going now. Oh, I have 1 minute and 17 seconds left. Okay. This is just to show how you get those Guest-Hutchinson nonlinear modes, and I will leave that. I'll also leave that. So now there are a lot of other things that have happened. I've focused only, on the simplest things. This square lattice behavior has these points in the Brill-1 zone that are topologically protected, and they move around and disappear depending upon the geometry here. This is, the pyrochlore lattice actually has the analog of these Weyl modes in 2 dimensions, only now, these Weyl modes in 2 dimensions are characterized by a non-vanishing winding number of the determinant of C going around there. So now if I go to 3 dimensions, I can imagine this line coming out of the board like that, or out of the side. And what I have is the analog of a vortex in this funny lattice spacing, and that's what's drawn here. You can have any lattice that has 4-fold coordination on average will have the zero modes on the surfaces and will have some topological property. So here's a lattice taken from a jamming problem. We also have lattices that are quasi-crystalline lattices that have the same property. And the interesting thing is that for the jamming problem, you have many different arrangements of the random systems here, and you will get different numbers of zero modes on the 2 sides depending upon the arrangement. So there is the possibility of a non-trivial characterization of the different jamming states. You can ask what happens when you put in a real dislocation, in other words, a topological defect in the lattice itself. What effect does that have on the zero modes? And you can have zero modes and associated states of self-stress that go with dislocations and disclinations. If you apply a stress to a lattice which is stacked like this, the stress will be concentrated on the states of self-stress. So if you want to localize where failure takes place in a lattice, you can put in these domain walls with the stress domain walls, and that's where your bonds will first break if you put in the weaker bonds or if you just concentrate the stress there. Okay, finally, just last 2 seconds. You always get -5 or something like that, don't you? So far, all I've talked about are the ideal Maxwell lattices. And obviously, if we're going to have any impact on possible usages of metamaterials for something useful, we need to be able to deal with the idea that we never have a perfect Maxwell lattice. So one of the mysteries of that transition is I've just shown you that these Maxwell lattices have the property that you can construct them so that one side is rigid and the other side has an excess of zero modes. Now, when I go to a true elastic solid, which will happen the minute I put these in at long enough wavelength, if I put in the bending forces or weak next nearest neighbor forces at long enough wavelength, they are elastically stable materials. And the elastically stable materials always have the same Rayleigh wave speed on the 2 sides. So how do you get from having nothing up here excess of zero modes down here to a situation where they both have the same behavior at long wavelength. So let's look at the case. So here, these are calculations done with V is the ratio of the next nearest neighbor strength to the nearest neighbor strength. So this lattice has V equals 0.1, and this is the non-topological one. This is the one where we had the same number of zero modes on the two sides. And you can see that when I've turned this on, here are the zero modes which lie below the continuum. The blue one is the top surface, the red one is the bottom surface. And they have the same slope down here as they should according to the elastic theory. But of course they are not, the two surfaces are not the same exactly. And at higher wave number, you see the difference by seeing a gap there. This is now the same thing at, I'm sorry, this is this is a non-topological one. B, that's this guy, is the same thing at V equals 0.001. So you get exactly the same behavior there, but the sound speed, the Rayleigh speed is smaller, and you get a much straighter dispersion. Now this is the topological one. This is when V is equal to 0.1. Now we have two surface waves in the red lattice, one of which is optical and just dies into the bulk spectrum, and the other now is the blue on the other side. Again, the slope is the same as they come in, and that's the Rayleigh wave. But when I go to V equals 0.001, so that's very small, we have the two modes, the two red modes, which eventually become this when we separate them a lot. And you can barely see it right here. There's a little slither of blue that goes up that far. And that is the Rayleigh wave on the top surface that has exactly the same slope as the red guy, but it dies into the continuum at a very small wave number. So that's how the system manages to fix that, and it's why we can still see remnants of the behavior of the ideal system in the experiments. So with that, I will stop.
Small statement. To invite to hand over on behalf of ICTS a memento to Professor Lubensky.
What is it? Am I allowed to look at it? Or is this something I have to look at? Oh, wow. Look at it.
You can take it by
Oh, look at that. Isn't that nice? Yes. Very good.
This is from Sandalwood.
Yeah. Uh-huh. So which of the this is a goddess, I believe. That's the Buddha itself. Right? Oh, okay. In his feminine stage, huh?
He's meditating.
Yes. Okay. Good.
Okay, I think we'll just go back to the question and answer.
Okay, so any questions here?
Hello. Yeah, so can you have systems where all the bulk phonons are localized, while only the boundary phonons, the ones which are topological, are the ones which are delocalized on the boundary?
Well, we have a one-dimensional system like that. Yeah, so we have something that we call a mechanical graphene. So that's a system where you take a honeycomb lattice, you put the center of mass of the triangle on the A site and the vertices on the B sites. So the vertices are shared by neighboring things, and you then put a spring, a vertical spring that's offset from the center. And so the modes that you're looking at are going up and down like that, and the spectrum and surface modes, everything replicates exactly the Kitaev honeycomb lattice under strain.
Other questions?
Yeah, this is probably a loony question. Do you think one could cook up anything analogous for materials with purely orientational elasticity? Imagine you had something which is 2D hexatic or 3D cubatic or something. Is there a chance, or do you need a lattice?
Well, and I mean, you can take the continuum version of this, and it has the property that along the topological lattices always have a q squared dispersion along one direction. And you can actually calculate the correct topological property by taking only the long wavelength limit there. But that still is an elastic system.
Right.
I don't know for sure. I don't want to say no, because there are lots of things that can happen. But at the moment, I don't have a good idea about that.
Hello, may I ask you? Kindly show me the slides of Cauchy-Riemann integral index theorem. Cauchy-Riemann integral index theorem slides.
Let's say it's the wrong way. Tell me when to stop.
Yeah.
Here?
Yes.
Yeah.
Hello, the n surface Q capital J in this way.
Yeah.
When I calculate this also for this topological characterization, this is the complex analysis for the topological characterization of a system. Yeah. So it is equal to NZ minus NP.
Yeah.
NZ equal, let me finish, my question has not finished yet. NZ equal to number of zeros and minus NP is the number of poles. But when I write and do the integration, let me finish. dfz by Ez, I choose a function in such a way and then integrate. But I never get ln dt cu of curl of how you get this. You kindly show me that at the end of the day, after your contour integration, it is equal to nz minus np. Then I will be agree with you.
Well, no, it is true that the theorem says it's the number of zeros minus the number of poles. And so what we do is we choose the unit cell in the surface here, so there's this gauge transformation. I lost that. There's a gauge transformation. You take basically, I can choose all kinds of different unit cells. And the unit cell, there's an e to the minus iq dotted into the translation vector in front of, that distinguishes the original lattice from the other one. So if you have an e to the iq in front, minus iq in front, it kills, it's the other way around. If I have an e to the iq in front, e to the iqa in front, it kills all e to the minus iqs that are in the system and gets rid of the poles. So, I mean, it's true that without looking at it in some detail, you can't see it. But believe me, it's precisely that construction that eliminates all of the poles from this zero guy, from all of the poles from this surface determinant are eliminated by choosing this unit cell. It's the same thing you do in polyacetylene. So if you take polyacetylene and you choose the unit cell, so you go, let's see. Oh, did I turn it off? Okay. Yeah, so, I can have this configuration or this configuration. So if I choose the unit cell, so I have this configuration, and I calculate this business here, then you have only Z terms. Right, so this is the one we look at. So Z is e to the iq, and with this gauge, you have only Z terms. But I could have chosen the gauge which starts here and goes to there. If I do that, I have 1 over Z terms. And what I need to do in order to go from here to here is to move this guy, and creating, I start off with a unit cell like this. In creating a unit cell that looks like this, what I can do is to move this guy to there. And that then creates the different unit cells. So if I start with this cell, I just move this fellow back to there and say, oh, I got the wrong cell. I meant to have this one. And that process eliminates the poles that might have been there. true.
There's a question there.
Sir, you talked about those soft modes in the Maxwell lattices, right? So where we get the soft modes in the edge of the Maxwell lattice that you talked about. For Maxwell lattices, you showed the soft modes that arises in the edges of the system. So is there is there any relation between the symmetry protected edge states in the topological insulator that we get?
I'm having trouble. My hearing is not as good as it used to be. So, yeah. Okay. Yeah.
Hello. Yeah. So you showed the soft modes in case of Maxwell lattices in your slides. So I'm just trying to understand: is there any relation between the symmetry protected edge states that we get in case of topological insulators, and is there any relation between those modes with the edge modes that we get in the insulators?
So, I mean, there is a difference between this and most of the electronic stuff in that, in the electronic systems, zero is not well defined, really. You choose it to be where your chemical potential is, right? Here, the zero is absolute because, it tells me about the uniform translations requiring a zero mode. So when we say zero energy, we mean absolutely that, and that means that the zero modes have more of a elastic character than a topological, finite frequency character. Now, I should say that there is a whole sub-industry that I didn't talk about of investigating, one-directional edge modes and classical phononic systems that replicate much more closely the sort of things that people look at in the electronic world. I don't know if that doesn't answer your question. Maybe you can come back after we're finished here.
Okay. Any other questions? Okay, so I had a question. Yeah. So, like most of the stuff you talked about, the metamaterials are made from this sort of macroscopic stuff made from in these 3D printers and all, right? But are there also, like right now, are there any real solid state things which kind of...
I think it's unlikely that we will get these strange asymmetries with, just atoms.
Okay.
Now maybe nothing's ever totally impossible. My guess is.
And if you can sort of see some sort of assemble them in some way, it's.
Right. I mean, the other thing that's true also is that these mechanical things really are, to an excellent approximation, the bonds are defined, and so you have nearest neighbor bonds and bending forces. And if I go to a real solid of any kind, there are going to be further neighbor forces, and since it's not symmetry that's determining things here, it's really the restriction to a set of phase-space states that you can get from those.
Okay, so if there are no other questions, let's thank Tom for a fantastic talk.